Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, Dr. Chris and Dr. Sarah. Now then, let's get to some questions now. We've got one here from Foxy who says, when we take vast quantities of oil out of the ground, what happens to the space left behind?
Yeah, this is a common thought. People think all these billions of barrels of oil we're boiling off and burning off and putting into carbon dioxide in the atmosphere all the time must take up enormous amounts of space underground. And when you remove that oil, does this leave a gaping void in the ground? And does this make the planet in some way unstable? The answer is no, thank God. It doesn't. Most of the oil that's in the ground isn't in this giant sort of lake underground, which is how most people envisage oil reserves. In fact, the rocks that contain the oil are, if you like, permeable. They're like rocks with lots of little holes in them. So the oil is soaked into the permeable rock, in the gaps in the rock. And so when you suck the oil out, all you do is to leave what looks effectively like coral, so lots of spaces behind. And usually the oil's under pressure, so it wants to come out anyway. And then in order to get the rest of the oil out, the oil companies will inject a substance which doesn't mix with oil, usually something like water, for example, and this pushes the oil up the oil pipeline and replaces the oil deposits with the water. So actually you are putting something back in anyway, and the rock that you're drilling into to get the oil out isn't there isn't a big gap in the rock. There's just lots of relatively big spaces formed by lots of little spaces joined together. So the rock is very porous, is the word I'm looking for. So I don't think there's too much of a danger of the Earth's crust being destabilised, because given the mass of the Earth, which is about it's 6 times 10 to the 23 kilograms, the Earth. So that's a lot of mass. And the crust is the outer rind, and the oil is a drop in the ocean, literally, of that mass. So we're not doing anything more than just scratching the planet's surface when we take the oil out. Taking coal out is a bit of a different matter, because very often with these big coal seams, you have to leave big pillars of coal behind to prop the roof up, because if you don't, you get what happens to some people in Yorkshire, where they live near old coal workings that weren't properly managed, and their garden disappears down a coal shaft. And they wake up in the morning and they have a coal seam in their garden, well, what's left of one. So yes, you do have to be a bit careful with things like coal, but there you're removing rock effectively, and you're not leaving anything. There's nothing left behind to hold the seam up unless you purposefully leave big pillars of coal behind. So rock with oil in it, probably a lot safer.
Right, thank you, Dr. Chris. Tony wants to know what cancer actually is. Can you explain for us, please?
Well, why don't I talk about what's going on at the level of individual cells, and then Sarah can explain a bit about what happens in terms of the whole body. What we know about cancer is it's a genetic disease. So when you have a cancer, some genes that control the growth of cells have gone wrong. So in your cells, you have your cell's recipe book, which is your DNA, and every single cell in the body, with the exception of our red blood cells, have a complete copy of our entire genetic recipe book. And included in that genetic recipe book are genes that tell cells how to grow and also how to stop growing and also how to repair their DNA. Because all the time that we're alive, metabolism and other things and sunburn are producing chemicals that can damage DNA. And the damage means that you get mutations, changes in the genetic message, and you have enzymes wired into your cells that go along the DNA checking it, and they can spot these changes and they correct them. The problem is that if you damage the enzymes that do the corrections, then you can no longer correct the damage, and cells can accumulate more and more of these mutations until eventually the genes that control growth and growth arrest when cells are turned on and turned off for growth, those genes fail and they go into overdrive. So cells begin to grow uncontrollably. They don't obey the normal signals in the body that tells them when to grow and when not to grow, and they also stop observing normal tissue boundaries. And what I mean by that is that normally when a cell touches another cell, that tells the cell, right, you've run out of space, stop dividing, you must be fully grown. But in cancer, the normal growth arrest doesn't happen, and so a cell just goes, I don't care that I'm touching other cells, I don't care that there's no space, I'm going to grow straight through here anyway. And the cancer cells also activate lots of other degradative enzymes and things. So they pump out factors that can erode tissue, and they cause tissue to break down and cells to die. And this enables them to go around like a bulldozer, bulldozing their way through healthy tissue until they meet a blood vessel and when they get into a blood vessel or a lymphatic vessel, these are tubes that carry fluid from tissues back into the bloodstream, they can then break away some cancer cells, go in the bloodstream until they get to a different part of the body, and then when they get there, they can take root there, and that's how cancer spreads, and that's called metastasis. And that's usually why people die, because the primary tumour can often remain very, very small and insignificant, but it's this distant spread, the metastasis to other tissues, that often causes most of the problems. And they can be varied according to whatever organ is affected by the cancer.
Yeah, absolutely. I mean, if you take, for example, a breast lump, a lady might come to her GP complaining that she's got a breast lump, or one might be noted on a mammogram, and then you then go in and try and biopsy it to try and work out what sort of a tumour it is, and then what needs to be done about it. And unfortunately, for some people, you do find that has then spread into their liver or up to their lungs, or sometimes even to the brain.
What about getting rid of it? How does that work?
There are two ways of getting rid of cancers. One is chemotherapy, and the other is radiotherapy.
And surgery, of course, to remove the...
And surgery to remove the primary tumour, wherever it might be, whether it's in the breast or the bowel or whatever. Now, chemotherapy, that's drugs to treat cancer cells. So the aim with those is that generally they're injected through a vein. You set a drip up and the drug drips in gradually over a period of hours, and that aims to then try and kill off the cancer cells. And people will have a regime of chemotherapy over a number of weeks, targeted at their particular tumour.
Does it just hit the cancer, or does it hit healthy tissue as well?
The aim is that you hope it will hit the cancer cells mainly, but unfortunately you do get some nasty side effects from some of the drugs used.
Things like hair loss.
You can feel sick, you can get skin rashes, sore mouth, bowel changes.
Why does it cause your hair to fall out and stuff like that?
Yeah, that's because the drugs are damaging other cells in the body, and so the normal cells then aren't functioning properly, and so a proportion of them will carry on functioning properly, but some don't, and so
the
you then get the
radiotherapy?
side effects. Radiotherapy's different. That's using X-rays to target cancers. So the X-ray doctors will target X-ray beams towards the tumour to try and kill off cells. And again, you hope that you'll target just the cancer cells, but sometimes there is some damage to surrounding tissues, and you can end up with some burns sometimes and side effects from that
How do
as
we
well.
know, and what advice do you give to patients whether or not they're cured when they've had a cancer?
Yeah, I mean, it depends on the sort of cancer it is. So hopefully their cancer specialist, that's somebody called an oncologist, will advise them on the type of cancer they've got and what the chances are of managing to cure it, because it really does vary. Some tumours you can have, up to a 95 to 99% cure rate, and other tumours might be very low, 5 or 10% rate. So that would be discussed with the patient by the oncologist, and you follow patients up. So after their course of chemotherapy or radiotherapy or both, and surgery, you then follow them up with ultrasound scans or CT scans or MRI scans to try and check at intervals, maybe every year, maybe every 5 years, that the cancer hasn't come back again.
How are things looking these days? I mean, are we getting better at controlling cancer?
Yeah, I think nowadays we're a lot better at treating many, many cancers, and people that would have died in the past sooner are now living a lot longer. So I think generally the outlook for many, many cancers is a lot brighter than it used to be. And so it's not necessarily a death sentence, because I think people hear the word cancer and they're absolutely petrified. But there is a lot that can be done now.
A little email that's come in here from Gus. He says, question, could teleporting ever be possible in a beam me down Scotty way?
Teleportation's a difficult one. The bottom line with teleportation is, what you're saying is, could I take all of the atoms in a human body, could I dismantle them and then chemically reassemble them in exactly the right order and the right relationship to each other in another place? Very, very difficult, given that there are so many atoms in the human body. In fact, there are probably more ways to arrange all those atoms in a human body than there are atoms in the entire universe. So I think the chances of being able to beam me up Scotty in the near future are absolutely zero. But we can actually use various tricks of what we now understand about quantum theory to achieve small-scale teleportation in terms of particles. But in terms of a whole human, definitely not at this stage, I'm afraid.
All right. We have a question from Malcolm. He's on the phone. Hello, Malcolm.
Hi, Sue, how are you?
Yeah, I'm very good myself. You're through to Dr. Chris and Dr. Sarah.
I was discussing this question with a couple of scientific people some years ago. I said to them, what is the extent of the universe? And rather to my surprise, they each had the opinion that the universe was finite and expanding based on the Big Bang Theory.
Yeah.
And I said, well, that can't really be so, because if it's simply expanding and it's finite, there must be something outside it. And they said, well, don't be silly. And I said, no, I'm not being silly. I can't possibly conceive of the idea that there can be nothing outside, because nothing is space.
Yes, it's the big question everyone asks is, if the universe is expanding, what's it expanding into? What we understand as the universe is everything that exists, and therefore, if it's not in the universe, it doesn't exist. But it's very difficult for someone to conceive in their mind of how something can be everything, and at the same time, its boundary defines what exists, but what is it expanding into? I mean, it's very hard to get your head around. But what we do understand about the universe and its origins is that it's roughly 14 billion years old, this universe that we live in. It sprung into life about 14 billion years ago. Exactly as you say, there was a Big Bang, and the Big Bang started from a point in time and space which was infinitely powerful and infinitely small, and in the matter of less than a second, all that enormous amount of energy was converted into mass, so stuff, matter, that makes you and I up. And in fact, they don't really understand how that happens, but the Large Hadron Collider, which is this particle accelerator at CERN in Switzerland that has its own power station pretty much to run it, will switch on hopefully this year. That's going to be approaching the kind of energies of some aspects of the Big Bang when it collides protons, positively charged particles, together in a beam. And the idea is to try to understand from colliding these particles how energy turns into matter. That's what the scientists are going to be trying to find out at CERN when this machine goes live. In terms of the universe's expansion, the big question is, we know that the mass, the material that makes us up and the planets and the stuff we can see, if you do the sums, only equates to about 5% of the mass of the universe. So that leaves the question, well, what's the other 95%? Well, the other point is that there's stuff we can't see, and this is called dark matter, and this is probably responsible for gravity. And we know that there's a lot of this dark matter out there in space. There's a big blob of it in the middle of the Milky Way galaxy, for example, and this is responsible for pulling the universe towards itself. Well, if there's dark matter which is very, very massive, and it's pulling things together, but the universe is getting bigger, and we know the universe is getting bigger. How do we know that? Because you can look at stars, and in distant, say the Andromeda galaxy, for example, and you can look at those stars, and if you look at them, the light from them is what's called blue shifted or red shifted, depending upon what they're doing. Yep. And in the case of distant stars, it's all red shifted. So in other words, the stars must be moving away from us. That's because the light from them is being stretched out, and if you make it stretch out, then it must get more red, and that's how we know they're moving away from us, so therefore we know that space is expanding. Well, if the universe is expanding like that, why is it expanding? There must be something which is pushing the universe away or making it bigger. And this is where the other 75% of the mass of the universe is, and this is dark energy, and no one understands what this is. This is some material which pushes the universe apart. It makes up about 70+% of the mass of the universe, but we haven't got a clue what it is. We haven't got a clue how to measure it, and scientists are only just beginning to grapple with what it actually is. And here's the really hard thing to get your head around. It seems that when the universe expands and makes some more universe, it makes some more dark energy. So how does that happen? We just don't know. It's really difficult to understand, but that's exactly why we pay scientists to try and study this stuff.
All right, Malcolm, thank you very much.
Many thanks.
Thank you, take care. John in Colchester had laser eye surgery to correct his short sight, and he was wondering how the laser is created and used so precisely in surgery.
Well, this is all down to computers, because if we didn't have computers to work out where to shine the laser and how much tissue to take away with the laser, then it wouldn't work. The way that laser surgery works, and there's a number of ways of doing this, one of them is called LASIK, which is laser in situ keratomileusis. which is a posh way of saying you use a laser to etch a hole in the front of your cornea of variable thickness. Now, when you look at someone's eye, the way in which the eye works is that light goes into the eye, and about 80% of the focusing power of the eye is the front part of the eye, the cornea. And then the lens, which sits behind the cornea, takes care of the final tweaking, the kind of fine-tuning to get the light so it's accurately focused onto the back of the eye, the retina, where light waves are converted into electrical nerve signals that the brain can decode and show to us. That's how we see. Now, the problem with sight is that as you get older, or if you're born with a preponderance to develop a sight defect, what can happen is that the lens fails to be able to accurately focus light onto the retina, because the light should be focused to a spot on the retina, in the same way as if you focus sunlight with a magnifying glass, you can focus the light with the magnifying glass to a spot and then burn a hole in a piece of paper, for example. That's basically what your lens is trying to do with the light going into your eye. It's focusing it onto the right part of the retina very accurately. Now, if your lens cannot do that, if the lens is too powerful, for example, if it focuses the light too much, then the light is focused in front of the retina, and it then begins to spread out again before it gets to your retina, and that makes the image blurred. And similarly, if your lens can't become strong enough, and this is what tends to happen as you get older, then the light is focused behind the retina, and again the image is blurred, and that's long-sightedness. So with short-sightedness, one of the ways you can tackle the problem is to make the cornea a little bit weaker in terms of its ability to focus light. So you take your laser beam, and often they use things like a YAG laser, yttrium argon laser, and various other phenomena-making lasers, and you create a laser beam, and you don't release the beam or power the beam at the eye continuously. You release very short pulses, and these last for microseconds, very, very short amounts of time, and you use very, very accurate focusing so that the laser beam is directed just at the front surface of the eye, and it cuts or blasts out tissue of tiny amounts, slivers, less a cell or just a few cells thick, out to multiple layers of tissue, so that what you do is reshape the front of the eye, and it's a bit like reshaping a magnifying glass to change how strong it is. And the result of that is that when light goes through it in future, it gets refracted or bent slightly less, so the cornea is less strong in terms of its ability to focus. And then when the light goes through the lens, the rest of the focusing kicks in, and the result is that the light is accurately focused onto the retina. And by making accurate measurements of how thick the cornea is, how thick the lens is, and how good the focusing of those relative structures is, a computer program works out which bits of the eye to cut away and how much of it. And when they finish the procedure, the surface layer of the cornea, the epithelium, is folded back over the site, and that protects it, and it all heals up very, very fast, and then you can hopefully see a bit better. The downside is that if you have a really, really severe eye defect, and I think Britney Spears had eyes that were minus about 8 or something, really, really, really short-sighted, and she had it done. There's a danger when people with that degree of short-sightedness have their eyes done like that the cornea can become much weaker, and as a result, when you get a bit older, the cornea can bulge, and this can make your sight get dramatically worse. So it's not without risks, this procedure. It can cause loss of sight, it can cause abnormalities in terms of how well you can see, but in a large number of people it also produces a very much better outcome, which is that your short-sightedness is made dramatically better. By no means permanent, though, because if your eyes continue to deteriorate, you could end up short-sighted again.
Thank you very much, John in Colchester. I hope that answers your question. Bernie is on the phone. Hello, Bernie.
I heard a wonderful story this morning. I've got a diesel car, and a bus company was running on diesel fuel mixed with urea, artificially manufactured. I couldn't believe it. How does it work? What's the difference?
This is an intriguing one. This is a hard question. I don't know why you'd feed urea to an engine as a fuel source if you've made it artificially. I mean, urea is the way the body loses nitrogen.
Yeah.
So when we eat proteins are made of amino acids, which are building blocks, which all get joined together. And the core, or the linchpin of an amino acid, that's why it's called an amino acid, is nitrogen. So the body can end up with a bit too much nitrogen, and it gets rid of it by turning it into something called urea, which is then excreted in urine. But the thing about urea, the actual chemical formula of urea, it's got a carbon atom with a double bond to an oxygen atom, and then off of the carbon atom is an NH2, so a nitrogen with 2 hydrogens twice. And so it's an organic molecule. You can make it dissolve in oily things, I think, to a certain extent, and this means it will dissolve in diesel. And when you burn it, what it will do is to produce lots of gas, because you'll end up with water and you can end up with nitrogen, and you can end up with probably carbon dioxide coming off of that.
Exactly. You're getting...
And the benefit, as we're about to say, is you're producing lots of gas, and when an engine works, what it's doing is turning a liquid that doesn't take up much space into gas, which takes up a lot of space, and that's what drives the piston down, and this basically generates power for the engine. And I think probably what they're doing is supplementing the fuel with the urea to produce more gas, and that's what drives the engine. And a sort of similar thing, there's a sort of Viagra for engines, is nitro. You know, when you hear about people talking about having a nitro injector on their racing car, a nitro injector, if you've got a dragster, if you want to get a bit of burst of power into your engine, you have a nitro injector, and what you inject is laughing gas, nitrous oxide, N2O, and this gets squirted inside the cylinder, and the high temperature inside the engine produces nitrogen and oxygen, which then, of course, supports the burning of the... So you're getting 3 molecules of gas where you had 1 molecule of gas, and the result of that is even more gas in the cylinder and therefore more power. So that's why nitro works. It's basically Viagra for engines.
They were using a 2-tank system, so it's obviously properly metered. It's not the same as reprocessing the fat and putting it in your tank instead of diesel, is it?
No,
Totally
biodiesel or fat reclaimed diesel is slightly different. And what you're doing there is you're taking vegetable oils, which are hydrocarbons, so carbon chains of about the right length. The problem with them is they contain a lot of gums and sticky molecules. So the way you clean them up is you boil it up with sodium hydroxide, which is an alkali, and methanol. And once you do that, you get a sort of ester, which is a linkage between the methanol molecule and the fatty chain, and that is rape methyl ester or whatever vegetable oil, methyl ester, and it burns like diesel. And that's where once you clean that up and separate it off the sodium hydroxide, which is in the water layer that separates out with all the gums and glues and sticky bits, then you can feed that into an engine and it behaves like diesel. But most of the time they work as a mix. You don't put that raw into your engine unless you own a Challenger tank. Apparently Challenger tanks have such high compression ratios you can run them on anything. But normally they run at a mix, so you put in something like 15% of the hybrid fuel, and then the rest of it you put in naked diesel, and then it runs okay.
All right, Bernie.
Thanks for that.
Thank you. Bye-bye.
Bye.
Dear Sue and the doctors, Chris and Sarah, now I've always wondered why there are so many types of cloud out there. There's autocumulus, autostratus and cirrostratus and many others. I can't say them all, Chris. Why is one cloud one type and another cloud called something different? What makes them different?
The highest cloud is the cirrus cloud, C-I-R-R-U-S, and that means a lock of wispy hair. So you'll know immediately what I mean by that when you look up in the sky and see these very wispy high clouds. The clouds that are big and stormy, and the ones that create thunderstorms and big rainstorms like we've had today, they're cumulus and cumulonimbus clouds. And it's all to do with how high they are and therefore how dense they are. And if you want a really good storm, what you need is a lot of very damp air rising very fast, or being forced to rise very fast, so that what happens is that the air cools quickly and condenses, and it forms this very dense cloud. So it's all down to actually how much water is there and how much water is concentrated in one place. So when you make hurricanes, for example, what drives a hurricane to form is that the sea temperatures over the Caribbean, the Gulf of Mexico, get to about 80 degrees. And they stay warm for a nice long time, and this causes lots of very damp, water-saturated air to start rising, and it goes straight up in the air until, as the air rises, it expands and cools until it gets to the point where it's cooled down and it can't hold the water as a vapour anymore, and the water begins to condense, and you get these big, bulky clouds. Stray water, which gets higher up, can form higher, wispier clouds, and those are things like the cirrus cloud. So it's all to do with how high the cloud is and how high the water gets and how much water there is there. And that's why you can also see multiple layers of clouds, because you also have sort of streamlining of the wind across the surface of the planet. Because if you were to do a sort of cross-section through the Earth's atmosphere, you'd see there are multiple layers of different temperatures, different densities, and therefore different amounts of water. And that's why, with winds moving different directions, those things, you can get this sort of stratification of cloud effects. There's also one other kind of phenomenon where you can get polar stratospheric clouds, and these are clouds which occur over the South Pole, and they are linked to the destruction of the ozone layer, and they are the ones that concentrate CFCs, the very bad for you things that are in aerosols and asthma inhalers and fridges. They don't do us much harm, but they're bad for us in the sense that they erode the ozone layer, and when you have a hole in the ozone layer, UV rays can come through and give us skin cancer. So that's basically clouds in a nutshell.
Right, OK. Clouds in a nutshell we have. Gary says, I heard you could get, or they think they can make a wireless electric plug like wireless internet. Is this possible?
Yes, it is, but it's not very efficient. The way it works is what Michael Faraday showed to be the case about 100 and something years ago. I think 1790 was around, a couple of hundred years ago. What he showed is that magnetism and electricity are pretty much one and the same. So if you have a magnetic field and you move a wire through it, then you'll induce an electric current to flow in the wire. And if you have an electric current flowing in a wire, you get a magnetic field around it. And this is where you remember people in their school classes and they can't remember if it's their right hand or their left hand. They're supposed to be doing sort of funny movements with their fingers and things to do these right hand and left hand rules and stuff. It's a left hand rule. You point your thumb in the direction of the current, and the magnetic field that forms around the wire forms in the direction of your fingers are pointing. If you put your hand into a fist, that's basically it. But basically, you can use that phenomenon to transmit electricity. So that's effectively how transformer works, and how some of these cordless devices that don't have a physical plug can get charged. You have a big coil which makes a strong magnetic field, and you then put another coil near it in the device, and the magnetic field induces an electric current to flow in the other coil, and that then charges up your device. And because magnetism can flow through air, you can get a magnetic field through the air, for example. If you have a strong enough magnetic source, then anything placed within that magnetic field can feel the magnetic field, and it can get a current driven in it. So what you do is you have a magnetic field which is changing, so you fire an AC current through it, for example. This makes a changing magnetic field, and then you put another coil in that magnetic field, and the current is induced in that coil. So it can be done, but it's not very efficient, and so that's why people use a bit of wire, because it's cheaper, and it might even be safer. I mean, we don't really know what the effect of these magnetic fields is really on health. I mean, we have some vague ideas they're okay, but we really don't know for sure.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.